Deep learning models all boil down to one thing: moving and multiplying huge tensors over and over. CUDA GPUs, Google TPUs, and Huawei Ascend NPUs attack that problem in very different ways. In this topic, we'll unpack those hardware ideas at a practical, intuition-first level, so you can see how each platform really delivers its performance. Modern accelerators all rely on parallelism, but they express it differently. SIMD means one instruction operates on many data elements in lockstep. That works well when every element follows exactly the same path, like applying ReLU to a big tensor. NVIDIA's SIMT model adds flexibility. Threads still share an instruction stream, but each has its own registers and can branch, which is crucial for real ML kernels. Matrix units and tensor cores push further. They execute many fused multiply, adds as a single instruction, giving huge speedups for matrix multiplies and convolutions. Systolic arrays are like a heartbeat for matrix multiplication. Each tiny compute cell holds a weight, while activations stream through the grid. As values pass from neighbor to neighbor, each cell multiplies and accumulates partial sums, then forwards data along. The key idea is data reuse. A single weight or activation is used many times while it's on chip, instead of being reloaded from external memory. Because communication stays local, TPU-style designs can achieve very high throughput with much lower memory bandwidth pressure than a traditional GPU-style architecture. H100 and H200 GPUs are really a hierarchy of parallelism. At the top level, many streaming multiprocessors, or SMs, let the chip run thousands of threads at once. Each SM packs lots of CUDA cores that execute SIMT instructions on vectors of data, plus on-chip memory for fast reuse. Inside those SMs sit tensor cores, which are specialized matrix engines. They accelerate FP8, FP16, BF16, and TF32 operations, delivering huge throughput for deep learning with mixed precision. To understand GPU performance, you have to think about how data moves, not just how many flops the chip can do. Modern GPUs like H100 and H200 sit on top of stacks of ultra-fast HBM memory plus caches and shared memory closer to the cores. Each level trades capacity for speed. Beyond a single device, NVLink and NVIDIA Switch connect multiple GPUs so they can share data directly, avoiding slow PCIe transfers and enabling large unified models. TPUs are built as domain specialists for one thing: massive matrix math. Instead of many flexible cores like a GPU, they use a systolic array, where thousands of tiny units pass partial results to their neighbors in a wave. Data is streamed from a unified buffer into this array, multiplied and accumulated with very little control overhead. That makes TPUs fantastic for dense linear algebra and convolutions at huge batch sizes, while GPUs remain stronger for graphics, irregular control flow, and more general-purpose workloads. XLA is the translator between your TensorFlow or JAX code and the TPU hardware. It takes your high-level computation graph and aggressively optimizes it before anything runs. It fuses many small ops into larger kernels, chooses how to tile tensors across the hardware, and decides memory layouts that minimize movement. The result is a compact, static program the TPU can execute extremely efficiently. The key requirement is predictable, mostly static shapes. Highly dynamic shapes limit what XLA can optimize. Ascend 910C and 950 are built around one big idea: keep data on chip and move it efficiently between specialized engines. At the center is a large buffer that acts like a shared workspace. Tensor units handle heavy matrix multiplications. Vector units handle element-wise ops like ReLU and normalization. Scalar units manage control flow, indexing, and lightweight math. Deep learning layers are decomposed across these units, with activations and weights reused from the buffer, which reduces off-chip memory traffic and boosts throughput and energy efficiency. Ascend's data flow strategy is simple. Load tensors from HBM as few times as possible, then keep them on chip while you do lots of math. The DaVinci core pulls data into a local buffer, and the compiler fuses multiple operators into one continuous pipeline. Instead of writing intermediate results back to HBM, values move directly through tensor, vector, and scalar units. Less off-chip traffic means higher effective bandwidth, lower latency, and more predictable performance, especially for deep networks with long sequences of small operations. You can think of GPUs as a busy intersection with a human traffic controller. Cars are like threads. They arrive unpredictably, and the controller issues instructions in real time. That's great for flexible branching code, but coordination overhead is higher. TPUs and Ascend NPUs are more like high-speed trains on fixed tracks. The route is planned at compile time, so movement is highly regular and efficient. You lose some flexibility, but gain predictable, optimized throughput for large, well-structured computation graphs. These architectures also encourage two very different optimization mindsets. GPUs lean on runtime decisions. The framework launches many separate kernels, each with some overhead, but with a lot of flexibility. That makes GPUs ideal for dynamic shapes, complex control flow, and rapid experimentation, even if you leave some performance on the table. TPUs and Ascend NPUs favor compile time optimization. A global graph optimizer fuses ops, decides placement, and builds pipelines before you ever run the model. You get higher throughput, but you pay with longer compile times and a stronger preference for static graphs. Stepping back, here's the big picture. NVIDIA H100 and H200 are classic GPUs. Many streaming multiprocessors plus tensor cores, scheduled dynamically, with deep cache and HBM. They shine when your workloads are diverse, dynamic, and framework-driven. TPUs center on huge systolic arrays fed by XLA's compiled data flow and a unified memory buffer. They're optimized for very large, fairly static, dense matrix workloads. Huawei Ascend uses DaVinci AI cores with heavy on-chip buffering and operator fusion, targeting enterprise AI with balanced, specialized compute. Across CUDA GPUs, TPUs, and Ascend, the mental model is the same. First, embrace parallelism. Real speed comes from feeding SIMT cores, systolic arrays, or DaVinci units with big, regular batches of math. Second, design for memory. Throughput is usually capped not by flops, but by how often you leave on chip memory. Reuse data locally and avoid wasteful transfers. Third, rely on compilers. XLA, CAN, and CUDA graphs translate your model into something the hardware can execute efficiently when your code is static, well-shaped, and optimization-friendly.